Okay, is everything fine? Okay, my friend, thank you. Are there anybody online? Oh, I see. Hi, my friends. Thank you for your patience. There was a technical delay. Our apologies. So, I started with discussion of errors. So, the problem of errors is so famous and so important that the United Nations urges moratorium of use of artificial intelligence in sensitive areas like people recognition. The formula outputs will inevitably and unavoidably generate, AI will, but this is combination, inevitably and unavoidably generate errors is a formula that goes from a report to a report. It's very much surprisingly. Another report, this is a report of Council of Europe, it's 2019, with the same, and they say errors of AI, a big problem for society. Because again, they can be dangerous, nobody knows who is responsible, nobody knows how to improve the situation, because large system we can retrain on immediate, and so on. And if you really would like to study this, please go to this artificial intelligence incident database. There's huge collection of examples of error. Of course, not everything. Examples of errors. Of course, modern generative methods generate so many errors that this database is overloaded. It's absolutely much more than the classical methods, of course, much more. Okay, it's in this database. Of course, the situation will improve, but the question is, will it improve? Absolutely. Will be resolved, will just slightly improved. No, the list will continue. Cortana, Alexa, passport checker, and so on. Facebook Translate, Google Tag, and so on. It's boring. Okay, then may I repeat, the errors may be dangerous. It remains unclear who is responsible. To avoid recurrence of detected error, a quick non-iterative system fix is required. Correction of errors should not damage existing skills. Very difficult requirement. Because even if you have a huge system, imagine you have a huge system. You have a very good supercomputer. You have a group of new tasks where the system made error. You have the whole database, all training set, all the training set for the previous training. You have everything. Imagine that we start, add these new examples with new answers and go. Maybe we'll generate new mistakes. It's possible. For Russian, I will say there's sort of story, Trishkin Kaftan, if you know. This is not important, just from elementary course of Russian literature. Okay. So the message number one. Ivan spent much time for that, therefore I will not be in detail. Errors of the main problem 2020 and this 10. 2020 means 2020s. 2020s problem. The main problem is this decade is AI errors. Now we're in the middle of this decay, and the situation does not change. It began at 2015, 2014 approximately, and then continues and maybe infinity. Errors are unavoidable companions of the data-driven AI. I should remind that there are two types of AI, rule-based and data-based, and there was a special discussion starting from 1956 in Dartmouth College, where AI was invented as a part of modern science. Of course, the idea was much earlier, but in 1956, it was in Dartmouth College. There were Minsky, Shannon, many other people, 10 great classics, and so this is. But the data-driven AI, now that we have more data-driven AI than rule-based AI, but errors are unavoidable companions of data-driven AI. And a new AI winter will come if you cannot find the solution of this problem. And only those applications will survive where errors are not very dangerous. For example, Google Translate. Excellent system, and the errors are normal. Nobody cares. Just edit, or Yandex Translate, or these avatars, TV avatars, and so on. Why not? Can be errors, and nobody cares, and you can be reclicked, and so on. But this is not about surgery and about a pilot. This is difference. Okay. So fundamental, where it comes from. This is unexpected software, but uncertainty in training data. To be up to include everything, for 100 attributes, we need like 10 to the power 30 training samples, approximately. Well, just corners of the cube. It's not compulsory. Sometimes we can be better. The uncertainty in training data, we never have enough data. And uncertainty in training process, because training process includes some random components. Can we correct random? Can we correct? Oh, first of all, to preserve existing skills, we at least must use the full set of training data. Much resources for each single error. New error may appear. Preservation is not guaranteed. And the probability of skill damage is unknown. Why? And now the famous guy with citation like 150,000, just now we measure people not by citation, but he's clever and at the same time has huge citation. David Danoka from Stanford, he told that in his Millennium lecture, he tried to be AI, data analysis. He tried to be data analysis Hilbert. Remember Hilbert problems. And he tried to state the problem. And he told that the problem is how to work in non-classical world. According to his definition, non-classical world means that the data are wide, not big, but wide. What does it mean? It means that there are less objects than attributes. In this situation, we cannot rely on any statistical learning theory statement. We cannot rely on statistical learning at all. Just can follow, that's my addition, to Feynman, Richard Feynman, advice. We can never be sure that we are right. We can be only sure that we are wrong. And it's, if we have an illusion that we are right, we should try to find where we are wrong. And this is a proper science. And this I should find Galilei, Feynman, from Galilei, this classical, great theoretical physics way. And this is, he told that this is normal. And this first comment. This is not necessary that the number of attributes is larger than the number of attributes is larger than the number of examples. No. For terrible situation, it's sufficient that the number of attributes is larger than a logarithm number of examples. It's much more gentle, this restriction. The post-classical world began long before this number of attributes exceeds the number of examples. When number of attributes exceeds the logarithm, it's sufficient for terrible behavior. Just I cite, it's not a compulsory, in many papers, it's my pleasure to cite my paper, but it's not compulsory here. Maybe more detailed. And the second, it's for one side. For another side, the number of attributes is a very strange measure. For example, if all the examples belong to a straight line in the attribute space, we have no high dimensional space. We have just a straight line. One. We have one dimension. If to play the two dimension, it was known already for more than 100 years, and I will return to this. And therefore, we will compare not number of attributes, but dimension of data set. And here we meet the strange guy, the strange object, dimension of data set. It's very difficult to define, but we intuitively we understand that the dimension of the number of attributes is something terribly overestimated. If you have, thank you. If you have 1,000 attributes or millions of attributes, that means nothing. Usually, for example, we work with some famous databases of faces, 60 dimensions, 64, and so on. So it's never is 1,000. And this is another paper I like very much. This is Professor Neurorobotics, Bach and Zinoviev. I am proud that my friends published this very interesting and very clearly written paper. So, therefore, we can draw these two plots and then say, oh, this is different zones of data views. This dimension on number of examples. Danoch area where dimension is bigger than the number of examples. Post-classical area, this classical area when n is bigger than exponent of d, it's exponent. The border is thick. It's not just a line, we should say the strip, of course, but more or less. Then and then Danoch area below the bisector. And then if you go to dimension of data set, n is never smaller than dimension of data set, of course. And therefore, below the bisector is nothing. Of course, dimensional data set cannot be bigger than number of points. Then post-classical area here, and again, the exponent and classical area is here. There are Danoha classifications, or more or less improved, but I like, because Danoha lecture is very well written. Just advise you just to find it. It's online. You can find Danoha lecture. So message 2. The post-classical world is around. Is around because dimension of data is very often bigger than the logarithm of data, of number of data points. Number of data points is because exponent grows very fast, and if you have, for example, dimension 100, then exponent of 100 with any moderate multiplier is huge. Therefore, the non-classical, this is where we live. But what UK have mentioned that in some advanced points, the blessing and cursive dimensionality effects appear earlier. But at least they are cursive. There are two sides of the same coin. Blessing. The curse of dimensionality is an old notion. The blessing of dimensionality was invented in 1990s by Paul Kayan. But Paul is not as famous as Danoha, because Danoha thought very loudly blessing and curse of dimensionality. Paul Kayan, very good researcher from Georgia University, United States, very nice guy, introduced this notion, curse of dimensionality. Bellman, when he studied optimization in large dimensional space, noticed that very quickly these problems become terribly difficult with dimension. You can very easily optimize in 1D. Everybody knows that. Even the function is not very good, but you can use many things from Newton. No, I shouldn't listen. Everybody knows. On the plane also not much difficulty. But very easy, very quickly, with dimension difficulty, right? And in dimension 10 already is absolutely terrible. And the additional problem, people realize that if you have multi-dimensional data set, then the difference between distances becomes small. And the points are concentrated on a sphere. It's very difficult to define the closest object, and this is very unstable notion. In one situation, this object is slightly changed, and another object will be the closest, and you cannot apply even neighbor logic. And nearest neighbor logic is the best, I should say, the best approach to classification to start with. Because if KNN does not work, you can give up. Redefine the problem. If KNN works somehow, then you can try to improve. And you always can improve, at least twice better. But if it doesn't work, therefore, this is very important thing. So what is it? Well, of course, this is trivial comment. Explain growth of combinatorial complexity. Stupid complexity. If you'd like to have, no, of course, this is, or you have taken this central point. There's 2 points, 4, 8. Very quickly it becomes huge. concentration of distances. This is a simple eight-dimensional cube. And the distribution of measure. This each needle corresponds to a vertex. And this is the volume of the cube. The space near vertices is empty. The space in the center is empty. And there is concentration near some sphere. Or near the median of the distance. I always remember, I not remember properly, the coefficient like 2/3 maybe of the radius of this diagonal. Diagonal length, like 2/3. No, like that's very, very simple task with everybody. I usually just forget. Vanya, what is the coefficient, the distance to the concentrations radius? 2/3, 1. Huh? One-third. So this is the diagonal, that half of diagonal. 1/3 of the, 2/3, sorry. 2/3 of the diagonal. You can check it is high school exercise, just because it's too simple for me. And it's not nice because I compare to the diagonal. Diagonal is square root is not. Okay. So concentration of the volume. I like this. High dimensional ball is concentrated near its border. It means if you have high dimensional orange, everything will be in its P. So in the data space, what does it mean? Again, this means that you cannot find for sure the nearest neighbor. This is the center, and the nearest neighbor, all the neighbors are here, concentrated. No, it's a very easy tip. Distribution of volume. Dimension 1, volume depends on the radius. Linear, dimension 2 is variable, dimension 4 is variable the fourth degree. Dimension 128, which is almost nothing. The interior is empty. And only the pill is more interesting, the theorem about equator, waste concentration, special name waste concentration. Waste concentration. Everybody is concentrated near, I should say, if anybody is convex body is concentrated near, so I'm not yet absolutely convex, but convex body is concentrated near its waste. So it's called waste concentration. The volume of the ball is concentrated near its equator. And there is, here we should ask the audience, each equator, because like infinitely many equators, the answer is each. Which? Every equator. Why? It means that the equator of codimensional 2 is also concentration in each equator of codimensional 2, maybe with slightly bigger vicinity. Thin vicinity is codimensional, and slightly bigger vicinity in codimensional 2, and so on. Okay, this is exactly the Maxwell distribution theory. Statistical physics lives here. And then it's like this because it's somehow we, the one and other T people, final theorem. It's difficult to check. Do you know that you can never check that two vectors are orthogonal. Can you check? No, this in real data, you cannot check that two vectors are orthogonal. Never. Because the inner product will always have some. Huh? Oh, yes. Huh? Yes. And then the question is, immediately after we fix epsilon for epsilon orthogonality, we'll find that every random sample from a sphere will be pairwise quasi-orthogonal, and this sample will be exponentially large, bigger than the dimension. And this is important. This is very important, and this is used in artificial, in data science and so on. This is the final theorem is here, but there are many people before. By the way, it's the same Paul Kainin and Vera Kurkov. And this is the greatest result of the blessing of the Kurkov analysis. This is statistical physics. All statistical. This is the main. On this slide, you can find all statistical, for the problem of statistical thermodynamic foundation of statistical physics. The problem was solved at the beginning of 20th century by Einstein. Gives it here. The level sets of energy in huge dimensional space. In huge dimensional space. In huge dimensional space is space, particles, many particles. Then there is microcanonical distribution in thin layer between U and delta U. There is energetic surface. And this is so-called like delta function of energy. So it's special name, microcanonical ensemble. Then there is canonical distribution, exponent minus beta U, that is generated by entropy maximization. Entropy appears here for given average energy. And for example, just to supplement uniform distribution sub-level information. Huh? No. Yeah, we can discuss this later. But you see, if you fix the energy and say maximum of entropy for fixed energy, no, it will be not microcanonical. It will be Boltzmann. Yes, and if you fix temperature, this will be free. This is minimum free energy. This is very simple exercise. It's just no, we can discuss this separately, but I should just sure. And this canonical distribution, uniform distribution in sublevel set, and microcanonical are the same in some sense. But this is very convenient. And this is very obvious from the very nature. Fixed energy. It's almost coincide in high dimension for a good exercise. What does it mean sufficiently good and almost coincide? Well, almost coincide, it means that the sum average are almost the same. Sufficiently good means some continuity. This is people who invented this. These simple theorems are not, this was not obvious because so great people did it. Maxwell, Boltzmann, Gibbs, Einstein. And geometric functional analysis that extended this to mathematics from physics was also Levy, Millman, Talgrand, and Gromov. Great names. It's not empty. It's very, very great results. And the basic dimensionality is a manifestation of so-called concentrations of measure. Measure is concentrated sphere. All statistical physics is based, and then very interesting, Paul Levy did not cite physical works. He uses this idea in very simple settings for spheres. And in this book, significant part of this book is about this measure concentrations on spheres. But he did not. Okay, and now it's our new person will appear, stochastic separation theory. We will study not just concentration of smooth distributions. We study fine structure of data cloud and thin layers. From concentration of a measure, concentration of distribution, to separability of finite sets. This is another step. Next step. To say that this Boltzmann-Gibbs revolution was people looked on particles. And then Boltzmann, Maxwell, and finally Gibbs explained people that it's very useful to use ensembles, smooth distribution instead of discrete sets of particles. Now data analytics came and said, no, let us return to data sets because we have too huge dimension. We have not enough particles to create smooth distributions. And therefore, this counter-revolution, let us start from data cloud again, from concentration of measure to separability in finite sets. Okay. Now, after this long, simple introduction, one formal notion. Let a data set will be centralized, zero mean, and whiten it. You need covariance matrix. This is a standard pre-processing procedure. I advise you always do this. You have a data set. Look on this, analyze data, analyze how how good they are, how reliable, many questions. And then first, centralize and calculate eigenvalues of covariance matrix. No, not centralize, standardize, divide on standard deviation, calculate eigenvalues of covariance matrix, and change coordinates to have covariance matrix 1. This is so-called whitening. After that, you can apply many advanced procedures. This is standard pre-processing. Okay, so therefore, a point is X is Fisher separable from a finite set Y with threshold alpha if X, Y is smaller than alpha XX. That means that the length of vector X is bigger than projection divided on alpha for all data points. This is a simple definition, and we should follow it further. Please pay attention. And immediately go to the real theorem about this. First, without formal definitions. Extreme points in high dimension. Extreme point. Let me recall that an extreme point is a point that can be separated from other, finite set, from other points by a hyperplane. For a finite set. Extreme point can be, or it's they are vertices of the convex hull, or just can be separated by a hyperplane. This is very natural. You can see here, these are extreme points. These points inside are not extreme, of course. Clear. Very simple notion. Absolutely necessary because you cannot do many things if you don't know the Crane-Millman theorem about that the convex set is a compact convex set, the convex hull of its extreme points. It's a great theorem that is through whole functional analysis, data analysis, Crane-Millman theorem. It is behind many things here. These are extreme points. Sorry? And then in high dimension, with high probability, even in exponentially large random sets, all points are extreme ones with high probability. When I first understood this, I was very surprised. Because you take extremely 100 dimension, you take, say, million of points, and then each point can be separated by linears with hyperplane from all others. It seems to be counterintuitive. Yes, this is the first. But second is even more important. You see, this separation can be done by the hyperplane orthogonal to the radius vector. And this epsilon, the separation threshold should not be small. Even you can take, we like to take 2/5 or 1/3, something like this. Epsilon is not small. Stochastic expression reveals the fine structure of thin layer. Well, for example, n100 and then less than 2,700,000, the set of m random points in n-dimensional Boyle is Fisher separable, each point from the rest, with probability 9.99%. No more. If it is obvious for you, it's fine. Huh?
I mean, if you take a high-dimensional sphere, it seems that the area of the measure.
Yes, but the spheric cap also goes to infinity. Everything goes to infinity. You see, how many, it depends. You see, this random points is a border. It's not any number of points. But this, you see, for n100, is moderate high dimension. If almost 3 million points, you can randomly select, and they can be, you see, this is, yes. Of course, in asymptotics, you say if you have million points for 10 million dimensions, nobody cares. But if 100 dimensions, you take 3 million points, it seems to be a sort of miracle. The tendency is clear, but the answer is surprising. That's what I should say. Tendency, yes, you are right. How that? And then the question is how to cope with errors in the non-classical world. So now we discussed Kerr's blessing of dimensionality, and now we return to our main topic, the correction of errors. Using these theorems are interesting not just for fun. Of course, without fun is not so interesting. but it's also useful as an instrument. Okay, what can we do? First of all, we can try to return to classics. What does it mean? As I told, it can be even in 100-dimensional space. You can find that the data feel like a straight line or plane, or something not very curved surface. And therefore you can say, oh, the real dimension is small. Therefore we really have no high dimension. And then we can return to well-developed system of methods for low-dimensional data. And there is a huge number of methods, approximation theory, very sophisticated separation methods, and so on, but only in relatively low dimensions. Then reduced dimensionality, principal component analysis, independent component analysis, principal graphs and manifolds, autoencoders, methods of the previous century with some model improvements. And this is just an example. Yes, what this is principal manifold. It's an illustration created by Andrei Zinoviev. This is cancer data. This is, you see, this is what two-dimensional principal manifold works relatively well. Data augmentation. Data augmentation, in some sense, is analog of data of reduction, because if you can, by smearing data, don't destroy the important information, then what does it mean? It's mean that you can reduce. But what is good? It's good that with data augmentation, if it works, we shouldn't create data dimensionality reduction explicitly, but be careful. If you create dimensionality reduction, you can control the quality. But if you apply data augmentation, it's much simpler, but no quality control. Because, but what to do if the classic return to classical is impossible? That's our zone of interest, because non-classical world is around us. We think, we are sure that there are only two choices: to retrain the huge system. It's not, we don't like it. Or just to add some small device. It might be physical, it might be software device, it might be some agent, to correct mistakes of this cluster of mistakes. Well, this is technical requirements. It should be simple first. Second, it should not change the skills of the legacy system. It should not change this system. It should allow fast, non-iterative learning, one step just. And it should allow correction of new mistakes without destroying previous corrections. How it should work? We should say, this is a system. Imagine this is a neural network, not compulsory. The inputs, internal signals, and outputs, and correction. So these signals go to corrector. Corrector decide, should we modify the rule using our experience of errors diagnosed before or not? There's a universal part, a binary classifier. But of course, the specific part is a modified rule. Modified rule, I cannot say how it should be because it depends on the mistake. But the universal rule is diagnosis rule. And this is a miracle. This is a Fisher linear discriminants, just orthogonal to the radius vector. Example works surprisingly well in high dimension. What does it mean? First of all, these discriminants are explicit and non-iterative classifiers. After the pre-processing, I told you, after whitening and so on, this is just orthogonal to a radius vector. May I close the door? I feel that I will. Okay. Simply separate mistakes from correctly solved example in high dimensions. What does it mean? We have a new point. Let's imagine this is an error. This is a point from the correctly solved examples. And you can just say, oh, this is a distance, and the orthogonal to the radius vector, we separate. And the alpha is a triple. We can, of course, we can draw this, and then x should be outside this excluded volume, where the mistake is non-covered. The miracle stochastic separation, of course, let's be a bit more. This is the only, there are many theorems. The only theorem I will give is very simple. Okay, let us probability distribution. Let's say this bounded. No long tail, just equal. And this is, let us assume that there is a maximum value of density function, exists density function. This maximum value, they should not be small. No, but should grow r is less than 1. This is shouldn't grow too fast. Maximum is smaller than this is 1 divided on volume is a uniform distribution, and this is geometric progression. And r is less than 1. Okay? Then let y is bounded by geometric progression, and this simple quality points. Then the probability that a random point is Fisher separate from the finite set. The finite set is arbitrary, no distribution for a finite set. No distribution. But probability that a random point is Fisher separate from the finite set, random point, x is random, is p1 minus 5, where phi. No, it tends to 1 is geometric progression. The rest is geometric. R is less than 1, alpha is less than 1, and there alpha is more than 0.5. This is a one theorem, and this is the example of the table. What we have, probability 0.99, alpha is threshold 0.8, R, these are in various dimensions. For example, requirement for N10, nothing good. For N50, almost 2 million points, almost 2 million. The maximum hardness, maximum of the density function may be bigger than the uniform distribution in million times. It's huge, maybe hardness may be huge. And there's 91 points. Not so big. For 100 dimensional, this is 10 to the power 12, and here is already almost million points. And for 200 dimension, it's huge, too huge, and this is 10 also. You see, this is how this stochastic separation works. In this simplest, not optimal, simplest. Simplest like for, and this is compared to uniform distribution. How to prove this theorem? Prove this very simple. Let's consider the finite set. This is a unit ball where the distribution is located. This is a random point X. These are points from the finite set. For each point, we have a finite ball, excluded ball, where X should not belong. Shouldn't belong. To be Fisher separable. It's threshold alpha. Volume of one excluded ball is less than this. Decays is geometric progression. That's all. This is the proof. Of course, it's maybe not trivial. For me, it's always very difficult to follow these simple theorems from the slides or from the black, but I need to write by myself. But this is absolutely trivial. Obvious that we have excluded balls where X shouldn't belong. And the joint volume of all these excluded balls is less than y multiplied by geometric progression. It tends to. And then this is just not to say halva without sweetness. Just example for video. False positive trained on number and false positive removed. First of all, first question people ask, we separate one or several. Is there any generalization? Of course, there's a question to the world structure. If the errors have the tendency to be clustered, yes, there is generalization. For example, here, hydrants, this is mannequins, and so on, are clusters. Therefore, when you train on 20 errors, you exclude 80 errors. Yeah, no having no training. This is false positive removed, false positive trained to use it for training. There is generalization. Surprisingly, there is generalization because the structure of the world allows us. Of course, if you attended previous lecture, if this is absolutely random errors with random field, there will be no generalization. But this is, and there is nothing is for free. If you remove false positives, you remove also true positives, introduce errors. But you see, this is a very interesting curve. First, at the beginning, you remove nothing, and then start to remove something. This introduced errors. But because you see here are almost 3,000 true positive, and 200 false positives. This is rather good. And the percent and the accuracy sense is rather good. And this is for various distributions, for many generalization. I should not speak about because it's, I say that this special moduli should be stochastic separation. Just for uniform A, how the number of points can be separated depends on the distribution. A uniform. See, here is on number of points is logarithmic scale. Then normal B, then exponential distributions, D arbitrarily log concave. No, arbitrarily log concave is the most general, but and this is a lower bound for probability. You see, here we see the structure of phase transition. The probability that the set is Fisher separable, each point from the rest. For small dimension, no, then jump and almost immediately one. This is very interesting. It's phase transition. This is really optimal borders. And of course, there are many degeneralizations. The most general result is for convex envelopes of finite number of log concave distributions. finite number. The finite number does not tend to infinity. It's very important. There are two messages. Stochastic expression is manifestation of the blessed dimensionality in moderate, already in moderately high dimensions, and simple Fisher characters work. Now let's go to the topic. Oh, I have 3 minutes. The time goes fast. I'm so sorry. What is the data dimensionality? If we start from given probability distribution, there's no problem. But there is people never understand this from modern education. We never have probability distribution. We cannot even have a guess about probability distribution. We just have a data cloud. And this is our real situation. If you look on the pedestrians, you don't have a probability this is pedestrian, this is a hydrant. No, you just have the reality. Then, what's the dimension of the finite set? This is 0 from very far and 0 from a small distance. But in 1901, Carl Pearson introduces the data approximation approach. He told that we can approximate data, and he selected linear manifolds for approximation, and here he invented what we call PCA, principal component analysis. I recommend this book. I don't like it very much, but maybe it's the best, nevertheless. No, because all the people. So approximating by straight lines and then subtract the projection and iterate. Data approximation by straight lines, the illustration from a Pearson paper. We have data, we have straight line. We minimize sum of the square of deviation. Like energy, like springs. And we have the first principal component. The closest approximation is divided scattering of projection, and so on. And then this is a sketch, not the best, because the real computational algorithms are different. But just calculate the empirical mean, calculate the deviation from the mean, and standardize to unit variance. Maybe not, it depends on the problem. Find the covariance matrix, find the eigenvectors and eigenvalues, rearrange according to the eigenvalues, compute the cumulative energy, select a subset of the eigenvectors as low-dimensional basis vector sets. Project data onto new basis. But everything is clear, but not this. How to select? The first rule is the most popular in statistical application is the so-called Kaiser rule. Or just select average lambda, and above average lambda is significant components, below average lambda. Or somebody says not lambda, let be lambda by half. No, why not? Just to have some. The Kaiser rule. I don't know, why not? But there is another rule, so-called elbow rule. Elbow means change of slope. Look on the slope, and the slope change significantly. You say that before the elbow, this is significant, this is proper base. Then, and this is perhaps the best method, but not so well known. Conditional number rule. Fine, we select the border, select the border eta. Let's say lambda 1 to 1 k is less than eta, except below eta delete. Why it's important? Because in many calculations we use inverse matrices and so on. This is the conditional, this is broken stick rule. Because the sum of eigenvalues is given, trace of the condition. Compare this to the broken stick, randomly broken stick. And when this lambda are above the size of the broken stick, except, and this that will be below, delete. And then, because this is a very simple calculation, just summarize a part of harmonic series. This is very simple. Broken stick rule. There's 4 definitions of PCA, but don't relax yet. Autoencoders. Everybody have heard now about autoencoder. Autoencoder is just a nonlinear caricature on principal component analysis. Because if you take this intermediate, the coder and the core linear, it will be principal component analysis. And if you take a nonlinear, it will be very general construction. But if you don't regularize, it's absolutely senseless, because you can approximate everything. Therefore, should not have 2 big Lipschitz constants, encoder and decoder. Therefore, regularize and combine the mean square error penalty for the approximation error with the penalty for large second derivatives. Why not? Fractal dimension, box counting. Huge family of box counting methods. I just give you one. When you take a grid, the number of filled cells and number of empty cells will be different. And then the limit, but limit in some special sense. Limit, but not up to 0. It's absolute slope of linear regression not very far from 0. Because the limit, because everything is finite, there is no limit. Okay, well, then here n is, no, for here n is 4. 1, 2, 3, 4. And here, just for example, box counting for 1D data, n is just linear, and dimension is 1. Let's calculate. Principal manifold. Sorry, this Bernstein. Here, Bernstein, this work on this manifold learning, I just should mention, not only here, of course, but it will be nice to discuss with him. Of course, principal manifold, this is data cloud curve. This is a first principal component, bad. This is smooth manifold, good. And this is without penalty, just a you can use very with high second derivative as again penalty for high second derivative. It's standard methods. And Fisher separability dimension is very important for data analysis. What we do, we just take the probability that the point y is Fisher inseparable from all other points. And for a database, calculate the average value of this p. What means average value? Some points are separable, that 1. Some points are inseparable, that 0. Every sum divided by the number of points will be the function of alpha. And compare this, for example, for n-dimensional sphere. Comparison of 2 functions gives us the evolution of dimension. And here is, I like this plot, just not all dimensions are published in special papers, but here is a small dimension. Comparing dimension with 26 popular database. Number of attributes. Kaiser rule is hugely correlated with the number of attributes. That's an empirical fact. I cannot do anything. broken stick is usually correlated with number of attributes in the Kaiser rule, despite of very different definition. And we say we take many databases.
Yes, 26 data sets and estimated dimension over there, right?
Yes, yes. And then we compare this study how on these 20 we had to take 26 dimensions and compare 26 data sets. For each dimension we have 26 value of this. We compare this and we find that correlation is the absolutely correlated number of attributes. Kaiser rule, of course, is smaller, but and broken stick also the same. Then then this is conditional number is absolutely not correlated with them. Conditional number is highly correlated with separation dimension, with Fisher separation dimension. Huh?
How consider or what? Thank you.
What the explained variable variance is very bad measure, I should say. From my practice, it's very misleading because it's absolutely. What is explained? What is explained? What do we need? Which is, if you have just absolutely random, without any law, nevertheless, principal components will explain variance, and again explain. And again explain variance. You see? This explained variable is not very good. Then of course, and the boy and the variance takes the threshold. It's the same question.
Yeah, thank you. I was just wondering whether this the third method, which is the given ratio of the eigenvalues, is somewhat connected to the explained variance.
I think they all are connected.
Okay.
Maybe the Kaiser rule even more.
Thank you.
Say that.
I think
Maybe
maybe
better
connected,
leave
but
this one
yeah,
here.
sorry. Sure. Thank you. So it could be connected, but not necessarily, because like consider a case where you have a very dominant eigenvalue and then big tail of small eigenvalues, right? So like if you're looking at explaining 99%, like you'll have those eigenvalues included, but at the same time, the conditional number dimension will cut you off like at the first component. So yeah, thanks.
Okay, so this is because it's this last slide. I just prepared the next lecture about dimensionality reduction algorithms and application of dimensionality reduction. But I should say, the relevant definition of data dimensionality depends on the problem. There's no universal definition, and the NPCA should be supplemented by the selection rule. And even simplest PCA has many versions. It's very simple, but non-linear PCA even more. And even famous has many different dimensions. That's all. And 3 references. After discussion with Ivan, we discussed just 3. And the collection, because for example, this here is, for example, this Python package is available online, and many other packages are also available online. Therefore, okay. I apologize for long speech. I tried to be fast. Ivan told me that I prepared too long speech. Like, huh? You know, but the speech will not too long, just 20 minutes, with some minor question. Oh, so So, and some break, like maybe 10 minutes extra. Questions, please. No. No, you promise. Okay, about entropy, no, I'm right. Yeah, I checked. No, just. No, this is very simple. Very simple. Just, maximum entropy for given energy is. No, this maximum is exactly canonical. Boltzmann canonical. Exponent minus u.
I have a question.
Yes, please.
So, in the end of the day, we have so many different definitions of a dimension. But if I have a problem, which one should I pick?
Which should I don't know. If you have a problem, let us sit and consider this.
So there is no general way. How do you pick a dimension?
No, I don't know a general way. But first of all, you should understand different. First of all, explore. The standard advice is explore. Don't run too fast. Explore your data. Explore your separability properties. Explore your dimension. Dimension is, I advise to start from, let us consider classification problem. Then, of course, explore classification, K&N classification first, and okay, one, not so big K. Usually we start from 1 to, say, 70. And no, for Fisher, yes, but also very useful is box counting for K&N. No, Fisher dimension, box counting dimension, and so on. You always, first of all, always start from standard preprocessing. Take data, calculate mean, centralize, subtract them, standardize, whitening, and so on. But you can make terrible mistake here, because the first principal component may be trash. And in many bioinformatic problems, the first principal component is trash. Why? Because the first principal component is real dirt. Is a, no problem, if people study cancer, the first principal component just collects lymphocytes and so on, just not cancer cell, just trash, blood. And then sometimes you start from 2 seconds, sometimes you start from the third. And this is special. And then if you start from the third, you understand, first, third, second, what is responsible for? We find the first is lymphocytes, throw away. Second is something else. Third, okay? Then calculate the conditional number and count the minor. Then work in this finite dimension. In this finite dimension, you can already apply box plot, you can apply Fisher separability, and so on. But the pre-processing, of course, is standard PCA without any doubt, supplemented by reasonable analysis of each principal component. What is responsible for? We just take and what is responsible for, calculate the histograms of various types of cells and so on. This is route and beacon. This is a special album. It's not how we work, how I teach my students. My students in data mining, And just one module, just for example, with students, we also students, so PhD students. During a semester, they, in addition to the course work and every time theoretical homeworks, they do for like 5, 6, or at least 4 special mini projects. For example, you have 2 data sets, cancer, not cancer, well, just some attributes. You should take 3 methods, data mining methods, to create 3 systems for recognition. Test, explain the difference, and say what is better. That is a standard task. Or no, so that, or study, take 5 financial time series and try to predict them. This is 5 course works of this, 5 small works. And they train, they use this. Even from the first task, they try 1 attribute predictor. Each attribute is evaluated by its information value. It works as 1 attribute. Then cross relations between 1 attribute predictor. So this is a long way. There is no king way. Just push over there, please. Yes, you can take mine.
So probably you will cover this in the next lecture devoted to the dimension estimation, but still I have to ask, are there any methods of evaluating how good was the dimension estimate? Like,
No.
no?
No, everything is like, no, there is no universal methods. No universal. Of course, the result, the final result, you should go with that. As I told you about principal component analysis, you select principal components, you evaluate the meaning of each component, you delete what is not necessary and so on. And then you have like 60 components you can work with, or 10 components you can work.
Okay, then I maybe can reformulate the question. So are there any methods known for their stable approach in like evaluating the quality of this approximation? Maybe some concrete method has this algorithm of verifying it.
The stability, of course, the first question is about stability. Is your estimation, does this estimation is stable or not stable? Second method is the meaning, the value. You look on something is senseless. Some dimensions are senseless, just delete. Even they formally are sensible, large.
Yeah, for example, I imagine the noisy data, for example,
Yes.
where essentially the data, for example, lies on a sphere, but since it is noisy, this is like a spherical layer, not a sphere.
Yes.
So the dimension may be way higher than it should be.
Yes.
So this is what I am trying to figure out how to estimate, like.
No, the filter in the case, no. Of course, if you usually say usually in the sphere, so there are operations of filtering. If you know what is usual, you can say, but you study time series, you say the small frequencies, large frequency noise, small frequency noise, or seasonality. Some is noise, and you have the concept. But there is one axiom of data mining. It should be written by big red books. Somebody's noise may be somebody's signal. And this is an extremely important sentence. Therefore, when you ask me, I can answer many words, but as the end, but don't pay much attention because somebody's noise may be somebody's signal. More, there are special information transmission for spies, then use noise on the pictures to send hidden information online. Just
Thank you.
Don't use this. Okay, please. Yes.
Just a couple of questions, if you don't mind. Well, actually, the first question is, again, a problem, well, it just stems from a problem that is being discussed among physicists, but it's just machine learning. Let's say you've got some slow algorithm that calculates the interaction between atoms and electrons quite accurately. This is, say, DFT or just ab initio method, density functional theory. Some very well, but very slow algorithm that gives you correct data. And you can just use that information as a data set and teach a neural network and try to make the so-called machine learned false field. But as far as I know, one of the key issues there is, well, at least one of the approaches is to somehow account for the conservation laws. Because in physics, we know there are conservation laws, but if you just grab the data from some black box, in that case, say density functional theory code, then you may be not aware of the existence of those laws. And so the question is, can it be incorporated and without strongly changing all those theorems? I mean, some symmetries in the data.
Okay.
And the second question is.
This is question by question.
Okay.
I can forget.
Yeah, sure.
First, then,
Thank you.
of course, there are some. We have, for example, just for example, just formally, let us have 10,000 dimensional formal as data space, but we know that there are, for example, 100 relations between data values. And the relations are not very simple, but this is all conservation laws and so on. This means that we really live on some manifolds there.
Sure.
And there are two approaches.
I'll just project, right?
First approach is just exclude everything, stay on the manifold. Second approach is penalize deviation from the manifold. That's all.
Okay.
And these are two approaches people use in the so-called physical information, where two my friends developed this.
Because yeah, but like just thought to, like, I think you had the work, you had some works where you actually do exactly that, like that you induce, the springs and stuff, like this approximation of.
Yes.
So like, I think that's exactly.
But this dumb penalty.
Exactly answers the
Yes,
question.
there's a penalty. Yeah. Yes. So there are two approaches. Either to exclude and work precisely on the manifold. It can be possible, maybe possible, but maybe not very simple task, very convenient. Yes, depends on the structure. And the second will just penalize the deviation. Okay. This is why this.
Well, actually, my question was rather about whether there exists or not something beyond these two. But okay,
no, just
the question.
Maybe you can invent if you see it. Yeah. Maybe I even know. Okay. But this is the most common approaches.
Okay. Yeah, thank you. Thank you. And actually, the second question is very much related to the first one. Let's take number recognition. This is just a classic. In that case, the data, except the labels like 1, 2, 3, 4, 5, and so on. So the data, some pictures, right? Some pixels and so on. And we would like to calculate, let's say we are interested in estimating the dimension in some way up to, say, conformal transformations, not big conformal transformations because they can just distort everything, but not infinitesimal, but reasonable conformal transformations. Can it be done in the same way?
Okay, so this is, there are many questions of this sort. Therefore, so for example, we can consider not data points, but the orbits of a group, and so on. There are many questions of that type. You redefine the space of the data. You usually consider orbits as a points, new points.
On metric, perhaps, perhaps a metric, I mean, For example, if you take 2 points, which represent 2 pictures, the distance between these 2 points is like the maximum deviation of the conformal
Yes,
transformation.
something like between two orbits.
Yeah.
I should say there are 2 methods. One method is just a section. If you have a group, you can say each of for orbits I select a section of orbits, and for each orbit I select one representative. It's it can work.
Okay, equivalence classes, right?
Huh?
Kind of equivalence classes.
Yes. As a second, you can select something like Hausdorff distance between orbits. We also, with Ruslan, we did this. It's a bit more expensive, but of course, much nicer. Because distance between orbits is much nicer than just section. But people prefer to work with sections. Usually what is difficult, not only it's not beauty, but there's some topological problem because this is a not direct product. Therefore, locally it works well, but globally the sections are also
not simply connected or something like that.
Can be a topologically complex surface and surface space. Therefore, but people prefer, like for example, when people work with faces and try to work with eigenfaces and eigenanalysis of faces, what they do? They select the section of an orbit, fixed eyes, and fixed line of the mouth. Just deform up to fixed eyes and position. To calculate, for example, first principal components, the first principal masks of faces. And then if you have like 20 first principal components, you can reconstruct almost each face. But using this section idea. Of course, there's a group, there's motion, homotheity, and some slight projective, because it's, of course, it's not exactly frontal, maybe some small projective transformation, but it works. But not globally in the sense of if you rotate too much.
If you see the back,
yes,
it
is not the face. It's not the face. Yeah. No, computer is stupid and say, oh, this is the face. This is much better. Okay.
Please consider sharing.
Yes. Something. It will decide something. Okay. Yes.
Yeah, I also had a question. This is about one of the last slides. Why do you think the condition number method correlates so much with the separation dimension, if I'm pronouncing it right, but it has relatively low correlation with Fisher dimension, which seemed like a quite similar approach? Well, at least to the degree that I understood it.
This one, yes.
Yeah, like here, there is only, okay, can you please repeat the last 2 methods, ScD and FracD methods? This is the dimension based on Fisher separability.
Fractal dimension is box counting.
Okay, can you please return back to...
Box counting has some non-zero correlation with separation dimension. Somehow correlated, not perfectly, but somehow. And this, with this.
So why do you think the condition number correlates so much with the separate dimension?
Why? I don't know. The proper answer is why. Do you know?
So the answer, as I understand, is this: separability dimension somehow measures the ballness or ellipsoidedness of your data cloud, because the closer it is to a ball in n dimension, the answer will be, let's say, n, right? If you have a slightly elongated, like ellipsoidal shape, the dimension number will drop, but still will be like close to the original n. So
What about
pardon?
visual?
Separability dimension. It measures how.
No, sorry, I don't understand.
Yeah,
What about whitening? Because whitening kills all ellipsoid shapes.
Right. Exactly. So like it measures, anyways, my point stands, how close you are to a ball. So, and therefore conditional number measures exactly this, like, you know, it takes the ball part of it, like the ellipsoid, right? You see, so like that's why it's so close, right?
Okay, so now this is maybe I will discuss because it's a bit vague from my point of view, because separability dimension is defined after whitening.
Well, yeah, this is also a good point because it should, like, for example, a ball in the dimension after the whitening.
Yes, it's not a ball. This is a finite set.
Well, yeah, but
And this equidistribution is.
the range in each dimension should.
Yes, so the equidistribution on a sphere and the finite in the white and the finite set are essentially different. But you can see finite set somehow, and this is equidistribution of a sphere. And then, unfortunately, I just said to save time, just there are some many pictures how they behave. It's funny. You can take papers and back on Zinoviev from online. There's many pictures of that type. How this what is the question? How they depend on alpha? Alpha is here. Probability the point is fixed inseparable from all the other points with a threshold alpha. And how this probability depends on alpha for a sphere and for a finite set. And this is, the question is, to which sphere separability property of this finite set is close. And conditional number dimension is very interesting because this is small dimension means a very different run from the, I don't know. Really, the answer is I don't know. Just empirical fact. The same fact is absolutely not clear why Kaiser rule on broken stick are so perfectly correlated with attribute number. Perhaps there's property of the human preparation of databases. Because we select more or less important attributes, and we have intuition like Kaiser said. Kaiser rule. And then, huh? No, I don't think Kaiser. No. This is, I don't know. But very often in data mining, it's very difficult to distinguish the mathematical facts from the psychological traditions. No, for example, if people are accustomed to prepare data in one way, there will be strong correlation with the number of attributes in Kaiser rule. It should not be, but it is.
Get a simple idea about that. So as long as you've rightly mentioned that the attributes were chosen by human, the creator of the data set, then why not randomly choose, say, 1/2 of those attributes, do the same for all those criteria for the dimensions, and then try to calculate the correlation matrix? Will it change strongly?
Maybe, I don't know. I should say that what is the bet of Kaiser rule? Absolutely terrible. If you just duplicate the attributes, the dimension, Kaiser dimension, will also increase twice. It's absolutely terrible because the real dimension does not increase. The same for the broken stick and so on. And conditional number does not change if you just duplicate the attributes. Therefore, the Kaiser rule increases proportionally the number of attributes, you just duplicate the number of attributes. It's the most important comment. And the separability dimension, the conditional number dimension, the box count will not increase. That is the main important fact. Okay, my friends, I should say that we can consider continue with people who would like to continue, but I think that if you just see because politeness, you can go.